Okay, so today I want to continue with 4.3, hopefully finish definitely need to finish 4.3 and then move into 4.4 on Monday. We don't have class on Friday, no class meeting on Friday for the inauguration of the new president of JSU. So no class on Friday. None of your classes should be meeting on Friday, at least between the time of like 10 to 3 or something like that. I forget what the time frame is, but this class falls into the time frame, so we will not be meeting. So the plan is to finish 4.3 today. So let's review what we've done so far with logarithms, and just really want to make sure everyone understands what a logarithm does for us. So the question is let's say we have this kind of equation, a raised to the y is equal to x. How do we solve for y when it is buried in the exponent position? Whoops, the exponent position. So we want, in the end, we want something like y equals something, right? So how do we explicitly solve for y when it's buried in the exponent position? That's the question that logarithms answer for us, because what a logarithm says is a logarithm exactly answers this question, right? What do I raise a to get x? And we've practiced rewriting these. And you may recall that the way to rewrite it is log base a of x is equal to y. So we had this like definition that said if you've got an exponential equation or an exponential equation and you want to solve for that variable that's up in the exponent position, this is what you do. And you know, that doesn't really like tell you exactly what the log is doing, though. It just kind of rearranges it, introduces this new notation, and that's just it, right? So I want to talk a little bit more about how logs are inverse functions of exponential functions. So let me write that fact down. Logarithms are inverses of exponential functions. Okay, so recall that what an inverse function does is it swaps the input and output. So if I say a to the y is equal to x, then the input is y and the output is x, right? That's what's happening. I'm inputting a y into this and it's outputting an x. Okay. The log base a of x equals y. Now the input is x and the output is y. So we can see that happening here, that they are inverses of each other because the input and outputs are swapped. But I want to make it explicitly clear how you would actually use a log on paper to solve an equation like this without just rearranging it. Because getting from here to here, it just kind of, there's some details swept under the rug. So I want to show this explicitly. So let's say we have ay to the x. What you can do is take the log base a on both sides of the equation. So I'll take log base a, I'm writing it in red to emphasize what's happening here, of both sides. Oh, what? Sorry, that red marker snuck into my hand. I wanted this to be in black, just like it was up there. Okay, so you can say from here to here, taken log base, this is how you would say it in words, log base A on both sides. Okay, good. Now we know from our properties from last time, we had these properties of logs. Property number 3 in the text. Let's see if I have it written down somewhere. This property here that says if the log base and the exponential base match, then they sort of cancel each other out, right? They cancel each other out and you're just left with whatever that exponent was. So that's a log property. That's going to tell us that here, the left-hand side, log base A with the base A exponential, they cancel each other out, and I'm just left with that exponent of y. And on the other side here, I'm left with log base A of x, which is going to be some number or something. So it's the same thing, right? Nothing is new here necessarily as far as like what I started with and what I ended up with, right? Just using that rule that I showed you last time to rewrite exponential equations in logarithmic form, but there's this step happening in between that we can, now that we have those properties, we can explicitly write this step down where I'm taking the log base A on both sides. Okay, so this is how the log cancels out. You can think of it as canceling out the exponential. Okay. So we also last time talked about evaluating logs. So not necessarily rewriting equations, but evaluating actual logs. Like for instance, just a quick reminder, like we looked at log base 10 of something like 100. How would you evaluate that? So the question here is to tell me what this is equal to. And you have to figure out what is 10 raised to some number is equal to 100. So remember, the question is 10 raised to blank equals 100. That's the question you're trying to answer for this. And of course, we know that it's 2, so the answer to this question would be 2. Okay, so this is actually evaluating logs. We did that last time too. So we know how to rewrite exponential equations in terms of logs, and we also know how to evaluate logs, and we also know these log properties, which I'll just quickly rewrite here. Log properties. Log of any base of the number 1 is equal to 0. Log base A of A to the x, the log and the exponential cancel, just giving us the x. A special case of that, when x is equal to 1, we have log base A of A, right? So technically the x in this case is 1, so the output here should be 1. This is just a special case of this. In fact, you could even argue that this is a special case. This is really like the star property here, because what if x is equal to 0, right? Then a to the 0 is 1 and x is 0. So really this is a special case of this too. And then finally we had like the weird property. Well, it looks weird, but it really says the same thing. Here, this is saying that the log cancels the exponential. I can say that in reverse too. I can say the exponential cancels the log. So if they've reversed order here in the way that you would evaluate this, it still evaluates to x. It's just saying that they cancel each other out. The log cancels the exponential, just yielding the x, and the exponential cancels the log, just yielding the x. As long as the bases are matching, right? Bases are matching. Okay. All right, so now we want to look at let me hang on. I want to get my papers out of order here. Oh, dang it. Where did that page go? Whatever, I'll find it later. Okay, so now we want to talk about graphs of logarithms. So we're kind of moving into now thinking of logarithms as functions. Oops, logarithms. And whenever you're thinking of a function in math for your purposes, you'll want to probably think about a few things like what does the graph look like? What is the domain and range of the function? How are the functions useful, like in modeling maybe? Like what kind of real world problems does this function solve for us? Or what kind of real world problems does it model for us? So let's start looking at those things. So before I just start plopping graphs down, let's think about what is the domain and range of logarithmic functions. So again, moving away from like log equations to now log functions. So let me just go ahead and write down some log function like f of x equals maybe log base a, just being general, of x. This is what a log function would look like. Just some generic log function. Okay. Well, in order to answer this, we can ask the question about exponential functions. What is the domain and range of exponential functions? And because we know that, and then we can just flip them, right? Because exponential functions are inverses of log functions. And what do inverse functions do? They swap domain and range, right? They swap input and output. So if we can answer this question, what is the domain and range of exponential functions? So like if I had some function f of x equals a to the x, what is its domain and range? Well, we know its domain is completely unbounded, meaning all real numbers. So I could denote that with that bold-faced R, like the R with the two vertical lines at the back. I prefer the interval notation. It's just preference, really. So domain is unrestricted for exponential functions, and range was restricted. Whoops, range was restricted. Remember that exponential functions can never give you 0 or any negatives. Exponential functions can never give you 0. They can get very, very close. They can get very, very close, but they never actually touch the x-axis. They never give an output of 0. That's why 0 is wrapped in parentheses here. That's the lower bound for these exponential functions, 0. And then, of course, they can explode off to infinity. No bound on this side, right? Okay, so that means the domain and range of logarithmic functions, we're just going to swap these. So I'll say domain must be 0 to infinity, and range must be completely unbounded. Okay, cool. So that gives us an idea, like some kind of starting place for log function graphs, because it tells us that their domain being only positive means that they must be stuck to the x values that are positive, right? So only in the first and fourth quadrant. I'll start drawing pictures now. And its range is completely unbounded. So what we're thinking is, here, actually, we can cover that up. Don't need that anymore. So what are we thinking? We're thinking log functions. Here's x and here's y. Must be, the domain is positive, 0 to infinity. So that means the x values have to be over here, right? So that domain tells us that the log functions must be in the first and fourth quadrant, if you recall the quadrant names, right? 1, 2, 3, 4. So log functions, by the way, log functions that have not been shifted or anything, right? Because of course, if you shift functions or flip them, that messes with the domain and range a whole lot. So we're not getting into that. We're just talking about a normal log function that has not been scooted or flipped or reflected, nothing like that. So a base log function has domain 0 to infinity, so its x values have to stay positive, cannot go over here because this is all negative x values. And its y values are not restricted at all, so it can go into the positive y values, no problem. All this stuff up here can go into the positive y values, and it can go into the negative y values, no problem. So we expect our log functions to stay over here in the first and fourth quadrant. That's all this really tells us, though. Of course, that doesn't like give us a good idea of the actual shape of the graph, right? Like at this point, we have no idea, right, what they might be shaped like. But what we can do is we can continue to use this idea about log functions being inverses of exponential functions. So consider that inverse functions sort of swap, this is saying it informally, but I suppose it's not incorrect. They swap x and y, right? Input, output, domain, range. They swap x and y. So if I know that the graph of an exponential function, here's x and here's y, a base, just a normal exponential function, I know its shape is like this. All right, and then it blows up to infinity like that. So I'll call this f of x equals a to the x. And then, okay, let me think. I want to be careful about this. Give me a second to think about this. Okay. And then what I want to do is I want to swap the x's and the y's and make them change places. Then what will the function end up looking like? So if I just like rotate this coordinate plane somehow, flip it over and rotate it so that x is vertical and y is horizontal, just for the moment, like don't let this freak you out, it's just for example, right? Just to show you kind of where the graph is coming from. So I've made x and y, the x and y axes, flip places. Then if I draw this graph on here, it will be the log graph. It will be a logarithmic graph because inverse functions swap x and y, and exponential functions and log functions are inverses of each other. So now what I need to do is I need to draw this function on this graph, and then I'll flip it back so that x and y are in their normal positions and flip the graph with it. This is going to be very tricky, but let me write this is negative x and this is negative y. Okay, so I draw, let me think, is this how? Right, yes, so I draw the function. And I'm not going to name it anything yet because this is like a bonkers like middle step, right? This is an intermediate step that is strange, but I'm making a point about the x and y's swapping. So for the moment, they have swapped, and then I'm going to change the input variable back to x and the output variable back to y, because we like to use them to represent input and output for both functions, right? Which is a little bit confusing, but so what is this function doing once I flip this back to this format here with x being horizontal and y being vertical? Down here, where y is negative and x is positive, it's sort of hugging this axis, right? Because this horizontal axis is now vertical. And then it comes up and it goes through the x-axis at the special point of here 0, 1. So this would be 1, 0 when it flips, and then it just takes off like that in the first quadrant. There it is. There is the f of x equals log base a of x, some generic log function. It flips it, right? These inverse functions are reflections of each other over over a center line. I don't think we've really talked a whole lot about what inverse function graphs look like, but this is an example of what inverse function graphs look like. They are very similar to each other, but it's like the axes have been swapped. So this is going to be the general shape for our logarithmic function graphs, this right here. This function, this is what you need to know right here. General shape for log graphs is just like this. So let me redraw it and then make some notes about it, and then we'll look at some specific examples in Desmos. So, and I do know that one special point that it goes through, so it hugs this, it goes through this point on the x-axis. Remember that all of our exponential functions went through a point up here at 0, 1. Likewise, all logarithmic functions are going to go through the point 1, 0. See how x and y have flipped, right? It was 0, 1 for all the exponentials, and now it's 1, 0 for all the logs. Okay. Let me label axes just since that's been getting a little crazy. So let me make sure we know this is a normal XY graph. There we go. There's the logarithmic function. So we know some things about these. We know that all log graphs will go through the point 1, 0. Again, this is all with the understanding that they have not been scooted around or flipped or reflected or anything crazy like that. Okay. Yeah. Okay. Their domain. So here are facts. I meant to write this in black, but oh well. Their domain is 0 to infinity. Okay, see, it never touches this 0 on the, it never touches a y value of, sorry, x value of 0. Sorry. It touches a y value of 0 right there, right? That's the coordinate point it goes through. Never touches an x value of 0, because remember, this y-axis represents where x is equal to 0, and it never touches that. Its range is completely unbounded. Okay, let's say that it does have a vertical asymptote where, well, right here on the y-axis. So it can never actually touch the y-axis. It's down here, it's going to get really infinitely close to the y-axis, but it'll never actually touch it. And over here in the top, it's going to keep growing unbounded both that way and that way. It's growing very slowly upwards, but it is growing upwards. It's growing just like an exponential function, how it increases like super fast vertically, but very slowly horizontally. This does the opposite. It increases very fast horizontally and very slowly vertically. And there is a Just like with exponential functions, there was a horizontal asymptote. Now, since things are flipped, there is a vertical asymptote for log functions. Okay, let's look at some actual graphs. Go to my, hang on, I'm going to share my screen. Always got some stuff open. Come on, let me open a new tab. What? Okay, that was weird. It wouldn't. Okay, all right. Here we go. Desmos. So when I type log here, it's going to want a base. So I'll say base. Let's start with base 2, and I'll say of x. There it is. There's a log base 2. And let's go ahead and label that point 0, 1. Oh, sorry, no, that's for exponential functions. I meant 1, 0, right? 1, 0. They're all going to go through that point. So let's look at a log base 3 of x. There it is. That's the green line. And then log base 4 of x. So notice they're growing at different rates, but they all basically follow the same shape, right? They're all getting very, very close to the y-axis as the, the x-axis. No, sorry, goodness, I'm going crazy. They're all getting very close to the y-axis as x gets very small. So as you make x very small, like very close to 0, the log function gets very, very negative. And then they grow, they pass through this point 1, 0, and then they grow unbounded very quickly horizontally and very slowly vertically. So I could pick like a very high base, like let's say log 10 of x, and it grows even faster horizontally, right? So it's growing vertically slower and horizontally faster than, say, this log base 2. And by the way, what is like log base 1? Remember, we weren't allowed to have 1 for the exponential functions. What if I try to do it for this? And it doesn't like it. It's not even, it's not even going to graph it. Yeah, it doesn't even like it at all. It doesn't want to graph it at all. Because this is asking the question of like, what do you raise 1 to? Anyways, it's a weird question, so we don't let a be 1. Just like in exponential functions, we didn't want a to be 1. We're not going to want a to be 1 for logs either. So there are some examples. What about log base? What's that special exponential function we had? The e function, right? And there's that one. Wait, where is it? Yeah, there it is. Not much more special than the other ones, right? Remember, for the exponential function e to the x, it was special because of its, not because of how it looks on the graph, because it pretty much looks like the other ones. It was special because of that limiting property it had, and also how useful it is for modeling things, how useful it is for calculus calculations. And similarly, the log function with base e, so sort of its counterpart, is going to be just as useful, even though on the graph, it really doesn't look that special, right? Okay. Alrighty, so let's start talking about some special logs. So pretty much what I want you to know for log graphs is right here on this page. Know the general shape, know that they go through this point 1, 0, know their domain, know their range, and know that there is a vertical asymptote on the y-axis. I'm not worried about like reflections and shifting log graphs. Okay. So now we want to talk about some special logs. Really, what I mean by special logs is special bases. So special values for a. We have log base 10 of x. So the a value is 10 here, is called the common logarithm. And the way we typically denote it is if you see a log like log written without the base of 10, then it's a common log. So it's denoted usually so mathematicians like to suppress notation wherever they can. And this is one of those examples. So it's like the square root thing. You learn about square roots, and then you learn that when the number is not written in the index position, then it's understood to be a 2 for the square root. It's a similar thing here for a log. If the base is not explicitly written, then it's understood to be a 10 for and this is called the common logarithm. So this gets its own name and notation because common logs used to be used to calculate to do like big like hundreds of years ago, logs used to be used to do big calculations, like giant products of numbers. There was ways to use logs to quickly do like big products of big numbers or something like that. So it's not used that much anymore because we have computers to do big calculations, and computers don't use logs. At least I don't think so, to do those kinds of calculations. So this common logarithm is not nearly as important as the next one, but it is still used. It is still used frequently enough that it still gets its own name and its own little notation. Okay, the other common log, or I'm sorry, the other special log is the log of base e of x. So this one is very, very important. Just as important as the exponential function is, the log with base e is equally as important. So log base e of x is called the natural logarithm. Just like you may have heard that I may have used the terminology, the natural exponential function for the e to the x thing. So this is called the natural logarithm, and it's denoted, so it gets its own notation. You'll never see like log base e written like this because it's going to have its own notation, and it's ln of x for natural log. ln for natural log. At least I think that's what ln means. I know that's the notation for it. I always just assume that n means like natural log. And on the calculator, these each get their own buttons. So for instance, remember earlier I said, I asked you, like as a quick example, log base 10 of 100, and that means like 10 raised to what is equal to 100, and we got 2, right? So, but now we know that log base 10 can just be written as just log, right? On the calculator, that's how the calculator sees it. So if I ask the calculator log of 100, it knows rather that I'm talking about a log base 10. Hang on. There we go. It knows that I'm talking about log base 10, so it should tell me 2, and it does. It does. And then the ln button knows that I'm talking about e, so if I asked it ln of 100, it's going to give me some crazy number. Because I'm asking it, what do you raise e to get 100? And that's e is like 2.718, so that's a harder question to answer. But what if I said ln of e raised to the third? Then it should give me 3, because the base and the exponent, or the base and the exponential are matching, so it should just output that 3. That's that property, right? Okay, let's do some practice with these. Turn this light back on. we'll do this example evaluating these logs. And then we will look at sorry, one second. We're going to look at a real world example. Okay. Say log of 0.01, log of 10,000, and C log of 13.49, log of -10. All right, and then some ln ones. ln of 1 over e squared. F ln of e raised to the 5th. ln of 175.2 and ln of 0. That's a lot. Okay. So the idea is, though, now that you know these are buttons on the calculator, right? Just use the calculator. So I'm going to cover up these so I have room to work A and B here. So A log of 0.01. So I'll say it on log of 0.01 gives me -2. So is that okay? It gives me -2. Yes, because the output for logs is unbounded. They can yield negatives. That's okay. You can't give it a negative, right? So log of 0.01 is equal to -2. Does this make sense? Well, keep in mind that 10 raised to the -2nd is 1 over 100, right? The base of this is 10, so 10 raised to this should give me this. 10 raised to -2 should give me this. Does it? Well, 1 over 100 is 0.01, 100th, right? So it does, so it works. Okay, B, log of 10,000 is 4. Does it make sense? Yes, because 10 raised to the 4th is 10,000. So I'm just like over here, just confirming that this is correct by rewriting it in exponential form. That's all I'm doing, right? This is not necessary because you can trust the calculator when it comes to these log base 10 and the ln, the natural log, because you have a button for it, right? But you should understand where the answer is coming from. Now, here's one where you cannot really maybe understand where the answer is coming from because it's not a power of 10. Log of 13.49. Now, I can tell you that I think it will be close to 1, a little bit more than 1, because I know that log of 10 should be 1, because the base is log base 10 of 10 should just be 1, right? Log of just 10 will be 1, and then log of 100 will be 2. So that means that log of 13.49 should be between 1 and 2, probably very close to 1. So let's see what we get. 1.13. We'll just keep 2 decimal places. So I'll say approximately 1.13. This means that if I raise 10 to the 1.13, I should get approximately 13.49. Let's see. So go. 10 raised to the 1.13 is, yep, 13.49 if I round, right? Of course, I'm approximating here, so it's not exact, right? But it's pretty close. Okay, what about part D? Log of -10. undefined. Can't say anything about this, right? Because I cannot give it 0 or anything less than 0. Let's see what the calculator does. Log of -10, domain error. Yep. So can't do that. Okay. Let's look at E and F now. E, ln of 1 over E squared. Well, I can plug it into the calculator. Ln of 1 divided by, and then I'll say E squared, close both sets of parentheses, and I get -2. So why is this true? Because E, which is the base of the log, raised to the -2nd is equal to 1 over E squared. Okay, part F says ln of E to the 5th. This one's a lot more straightforward. No need to, in fact, don't even need the calculator, right? Because E is the base of the log, E is the base of the exponential, they match, so I can just write 5. And if you don't believe me, you can go to the calculator, say ln of E raised to the 5th is 5. G and H now. Now, this one definitely need the calculator for, because this is not going to be a power of E, right? This is not like E squared, E cubed, 1 over E squared, anything like that. It's just some crazy number. So, whoops, let's say, whoops, goodness, ln of nothing to do, honestly, but just plug it into the calculator and see what it tells us. 5.17 when I round correctly. So apparently it's pretty close to E to the 5th. Let's see what E to the 5th is. E to the 5th is 148.4, so it's kind of close to 175, at least in the ballpark. Okay, and then finally part H says ln of 0. Now that looks like a domain error because I cannot plug in 0, right? But let's see, what does the calculator say? Domain error, domain error. So this is undefined. So you cannot plug in anything 0 or less. 0 or any negatives cannot be plugged into any kind of logs, whether it be a natural log or a common log or any base log. Okay. Now, give me 1 second. I need to find that page where I've written that problem. So the problem I opened this section with was a problem of trying to find time from a compound interest formula, right? And remember I said at the top of today's lecture that what logs do for you is they tell you how to get your variable unpacked from the exponent position, which is exactly what this question is asking. Wait. Yes, yeah, this question is asking for time, and time is packed up into the exponent position. But we can get further now, because now we have some tools, some algebraic tools, to be able to solve this maybe a little bit further. Let's think about this. What can we do with this from here now? Now that we know about the natural log that has base E, so I have 2 equals E to the 0.06 times T. So this is a question of how much time is required to double an investment and an interest. So we've already kind of worked this problem as far as we could. The point is it's asking for time, asking us to solve for T. What if I take the natural log on both sides? Let's see how much further we can get now. So I'll take the natural log on both sides. Why am I taking common log, or why not log of base 2 or something like that? I want to take the natural log because I want the base of my log to match the base of the exponential function that I'm trying to unpack. Let me say that again, because that's important when you're trying to solve equations like this. Let me write this and then I'll say it again. You want the base of your logarithm to match the base of the exponential function that you're trying to undo. So in my case, the base of the exponential function that I'm trying to undo is e. So I want to use the logarithm that has base e, and that is exactly this ln natural log function. So what does this do? Well, on the left-hand side, I just get ln of 2. That's a question for the calculator. That'll have to be approximated. But what happens over here? Any ideas? It's going to be a use of that property that tells me when the base of my log matches with the base of my exponential, they cancel out. So what's going to happen here is the log and the exponential cancel, leaving us with just the exponent. Why do they do that? Because the base of the log and the base of the exponential match. So all I'm left with is 0.06 times t. I can leave that in parentheses. There. See that? And now I can solve for t just using like high school techniques, right? Just divide by 0.06. So ln of 2 over 0.06 is equal to t. So this was enough. We now have enough tools to solve a question like this that asks for time from a continuously compound interest problem. So what I would do is I would say, to solve this, I'd say ln of 2 and then divided by 0.06. It's going to give me some answer, some weird decimal answer, but that's okay. So time is approximately 11.6, and remember time here is measured in years. Okay, so this is the power of logarithms. They unpack variables from the exponent position. Where it was unachievable previously, and now we have tools to explicitly solve for the variable that's packed up into the exponent position. So let's see, what else can I say? Yeah, that's pretty much it for 4.3. Okay, 4.4. Let me motivate that and then I'll let y'all go. So what is 4.4 going to be about? 4.4 is going to be about a bunch of log rules. You remember how you have a bunch of rules for exponents, like when you multiply two like bases, so you add the exponents, things like that. We're going to have analogous rules for logarithms from 4.4, but it's kind of going to culminate in this thing called change of base formula, where what we're going to look at is, what if you're trying to solve an equation like this, but the base is not e, right? Or the base is not 10, not some nice base. What if it's like 7, right? We don't have a button on the calculator for a log base 7. We've only got log base 10 and log base e. So what do you do if it's not those? What if it's 7 or 2 or 45, anything other than 10 or e? What do you do? And in 4.4, we'll see the answer to that question. Okay, so that's all I got today. That finishes 4.3. I'm going to have some questions ready for you for problems to mark for review. I'll be sending those in the chat or via email. Okay, so any questions about this section? Okay, I will see you guys on Monday, not Friday, on Monday.